Okay. Okay. There are two options. I could interrupt this for however long it takes to explain the entirety of directly mapped caches to you, and you can take a picture of this and work on it in the background if you want. Or I could not do that. Which one would you guys prefer? It'll take about like 10 minutes or so, maybe 15. First one? Okay, let's do it. Okay, what do I want? Doc.
No, the thing is like, first thing you need to know is like, what is the column represent?
Okay,
First thing is
so,
let's see.
for a CPU, so CPU runs really, really fast, even for memory. Memory is really, really fast, but it still takes a long time to read and write from and to memory, which is actually why we have multiple cores on CPUs, so that it can go back and forth between executing, because reading and writing from memory is actually that slow. So we have these things called caches, right? And one of the simplest forms is just a direct map cache, right? You have your memory address, like say for example 0x, I'm just gonna make this real simple, 1, 2, 3, 4, right? And then the processor looks at this address, and then if it's in the cache, it'll get it from the cache, so on and so forth, right? So let's say we read this address and we have a 16, I forget what it is, I'm gonna say row, with 16 bytes each in this cache, right? So instead of having the 8 rows with the 8 bytes each, I'm gonna do 16 and 16 just to keep things simple, right? So we have it, this table here, right? And I'm not gonna draw the whole thing, where you have these 16 rows, downwards, right? And you have 16 columns this way, right? And because memory is byte addressable, right, you have 16 like things per row, right? So this is like something something 0, something something 1, and so on and so forth, right? So to place this memory address in the cache, what you would do is you split it up as so, right? You'd have 0x, 1, 2, and then 3, and then 4. So this byte is disregarded for the purposes of a directly mapped cache, right? Because we have 16 columns, 16 bytes per row, right? We can disregard the lower 4 bits. This is why I wanted to do 16, so it would stay in hexadecimal, right? So the lower 4 bits, that doesn't matter what this is, as long as these are the same, it will be in the same row, right? Everyone get that? The math? So if you have 16 possibilities, right, you take log base 2 of 16 is equal to 4 bits. Yes, and then you ignore it. And then because you have 16 rows, you take the next 4 bits, which is the next hexadecimal address, right? So this would be in the 4th row because it starts at 0, right? So this would be the row you store it in, right? So then if you get a memory read for 0x1, 2, 3, 5, right, it would be the same row and would already be in cache. And the reason we have it where it's multiple bytes like this is because usually in CPUs you're accessing multiple bytes at the same time. Like pretty much all the time, right? If you're loading a word that's 4 bytes, not 1 byte or anything, and you usually like want to have the data around it, right? So you also have to store per row the tag, right? This thing here. You can still see it. So you want to store this sort of like left of here, and this diagram is going to get really messy, right? Because if you get 0x2235, right, it's the same row, but this is different. It's a different memory address, right? So if the CPU then tries to read this, right, it'll look at that row, the corresponding row in the directly mapped cache, and it will see that the tag is different, and therefore it's a different memory address in there, and it has to disregard that cache and then load it from the actual memory. Right. Does that make sense to everyone? Okay, cool. That's it.